I think at the end of this, my ultimate intent would be that everybody will maybe think a little more deeply and carefully about the data which they receive every day regarding polymer performance from their suppliers. We all know that materials test standards are very useful for understanding and comparing materials properties on a consistent basis, and certainly in the oil and gas industry, we hear reference to ISO and NORSOK standards on a commonplace basis, and I think the data generated from these tests is now pretty much a prerequisite for selling products into the industry. However, I think there are some considerable inconsistencies maybe in the application of these standards, and in this presentation, these slides, I would like to present various data collected by Victrex over the last 7 or 8 years to show how our test philosophy has changed in that period of time and how we aim to get the most useful data for our customers on lifetime prediction. So for the first part of the webinar, we are very lucky to have Alexandra available to present some slides on her experience of working with such tests. So I would like, first of all, to pass over to Alexandra, and then I'll be back with some further slides shortly.
Thank you, Jeff. So I would like to talk about some of the aspects of the NORSOK M710 standard, and they are equally applicable to the ISO 23936 standard series. And one of the common misnomers is that the standard is written as pass-fail type standard. It, in fact, is not. It's written as a test protocol. And the testing is specified such that it should be possible to use erroneous extrapolations. So that means in order for that to succeed properly, you actually do need to test to a degree of degradation in order to do some serious extrapolations afterwards. The protocol does not specify test temperatures or durations. It's entirely up to the user to define these based on material type and application needs or understanding of the material behavior. And it's also open for differences in testing and interpretation. And I think these things make it a very strong standard, but it also makes it inherently weak in the fact that you can exploit these openness to claim that you have passed NORSOK or ISO without actually doing very much testing at all, as we're going to be seeing in the next slides. So if you could, there you go. So one of the test setup challenges is that you don't have the specified temperatures, but you do need to have some kind of acceleration in order to get meaningful results. And also, it's no specified test duration, but it's within the standard, it's asked for at least a 50% reduction in properties. This is often interpreted as not more than, so if you pass the 50%, you're actually failing the test. It was intentionally made so that you should pass the 50% mark so that you get good degradation properties so that you can extrapolate with. But what we see in these graphs is that temperatures here have been chosen at such range where you see a change in properties between the 125 C and 145 C temperature range. So there is something going on, something either thermochemically or directly chemical that is changing on the different temperatures. So this set of data is really not proper to use erroneous extrapolations on, and you can see even on the right-hand panel that you do have some oddities, not as severe, but still you have oddities in your behavior over time. These data are for 13-week testing. If you go to the next slide, Jeff. Here's an example of extrapolation using our friend Arrhenius's approach, and it's a linear extrapolation. And if you see the yellow outlined line in the table, at 4 degrees, it's extrapolated to have 135,000.0 days degradation time. And just the fact that you have a decimal point in there when you in fact have such a long extrapolation from 65 to 135,000 is way past what our Swedish friend would ever have wanted us to do. And also, the 65-day mark is an asterisk point, so there were some issues with this particular data point. And if you see on the graph on the right-hand side, if you do change that point just a wee little bit, the linear extrapolation would be different. So you would have a different line through the data points, and that would significantly shift your 4 degree C data point, and thus maybe take decades or centuries on or off as far as the time to degradation. So this is absolutely not an exact science, and I think that's something that's really important for everyone to really understand, truly understand. So next slide, please. So another problem or issue, I don't want to call it a problem, but it's a challenge for us, especially with the high-end thermoplastics like the PAEK family of polymers. You typically don't see very much degradation at all. So you do your testing, and this is just an example, where you do testing and you end up with relatively flat curves. So again, our Swedish friend doesn't really have a good answer for what to do with a flat curve. In his approach, this would mean that your material would last indefinitely. And I think even in the oil field, indefinite is just a wee bit longer than we would be happy to claim our materials. So then it really does depend on how long you actually run your test for, if you can reasonably claim that you can extrapolate out to the service life or the material life of your particular material. But on the flip side of that, if we do any other type of immersion testing, normally what we do want to see is flat, so no degradation is usually a good thing. So I think that this type of behavior is going to be seen significant amounts of because of the types of material we're using. And for a steady degradation, this is great. You just have to keep in mind that if you are dealing with materials that will have abrupt degradations like chemical changes, fatigue issues that happen relatively suddenly, then you can't extrapolate beyond where you've tested, or you need to understand the degradation mechanism on a chemical level to claim life, because this type of testing doesn't really go beyond the last data point at 13 weeks. You can claim something beyond that, but you can't really say for certain. So that's something to be kept in mind. So as a summary, test protocols are really, really good and very powerful for learning about polymers and elastomers. And they do give very sensible output if you give them sensible inputs. If you have the correct temperatures and long enough durations, you will give very good results. But it's always important to keep interpretation in mind and to be very careful about extrapolations, because eventually some kind of degradation does happen. We know this for a fact, so we just need to understand it better. So with that, I think I've summed up my part. So here's the first poll. And the question is, are the materials that you purchase or specify today compliant with NORSOK or ISO standards, and you can answer yes or no or I don't know as far as your particular purchasing or specification goes. In my experience, most of the materials are specified and purchased according to these standards. I don't know if that matches with you, Jeff.
Yeah, absolutely. I think that that now this has become a kind of a prerequisite, really, for selling into the industry, and that's why I think it's important that we all understand what the test results actually mean.
Yeah, and what I see very often is that we have especially purchasers that ask for this certificate, but they don't typically ask for the data behind it, and there's no discussion about the interpretation of the data. So it's a stamp of approval, but there might not be significant amounts of understanding and contemplating behind that stamp of approval, and I think that's something that this webinar may actually do something about in a positive direction.
Yeah, exactly. So I think probably the poll is coming to an end now. I can't see the precise results on my screen, but I'm hoping that the answer is that most people are purchasing materials which are specified to those standards. Thanks very much, Alexandra, for those. Oh, there we go. Sorry, I can see the results now.
Yeah.
So,
Hi guys. We're just waiting for a few final responses that were in progress, and we should be able to see the results now.
Yeah.
So I can see 31% are saying yes, 3% are saying no, 16% are saying I don't know, and 50% haven't answered at this point in time. But that's a useful statistic, I think, to go on now into the remaining slides. And thank you very much, Alexandra, for your slides and
you're very welcome.
Introduction. So yes, as I mentioned on my introduction slide, the NORSOK M710 and ISO 23936 standards are probably the most frequently referred to standards in this field, and both of these deal with gaining an understanding of how a material, polymer material or elastomer, will perform when aged in contact with media used in the oil and gas industry. They are both very similar in their approach, in as much as mechanical test pieces are aged at least 3 temperatures in an environment, and the data is used both to demonstrate on a comparative basis how well the material resists chemical attack, but also to provide an estimate of a maximum operating temperature, which would provide a 25-year material lifetime. And it's important to mention there that that's a material lifetime and not actually a component lifetime. As Alexandra has said, it's very important to remember that this is not a pass-fail standard, or these are not pass-fail standards. They're simply test methods like any other, for example, like testing to ISO 527 for your tensile tensile properties. And they describe ways of presenting the data. So I think if we are going to talk about qualification in any terms for these tests, that would mean a lifetime assessment which shows that the material tested is appropriate for the proposed usage. So there we have 2 standards. We can use the data to compare the relative merits of different materials. And today I am going to present to you data from a range of Victrex products, but mainly our 450G polymer. And I hope to demonstrate the various anomalies and the various potential discrepancies there are within the test to present possibly confusing or misleading data. So moving on to both of these tests, they have a fundamental reporting requirement for both tests, and that requires some property data is presented by the supplier as documentary evidence, and also some quality control test data. And basically, this data would enable a potential user to make a judgment as to the basic suitability of the material for the job in hand, the proposed job. And it also would show that the material has been processed to an extent in an appropriate fashion. That would be from the QC data. Then for elastomers, there's a rapid gas decompression test. This isn't required for thermoplastics because thermoplastics are clearly far more resistant to rapid gas decompression. So we then move on to the aging test, which in my experience is the most discussed and reported aspect of either standard. And it's this aging test and the results therein which I will be focusing on in the coming slides. Excuse me. So the aging tests require that your material is exposed and aged in an environment which can be selected from a set of standard environments which you see on the left-hand side of your screen. And we age at 3 different temperatures in order to have sufficient data to be able to attempt a lifetime prediction. Clearly, additional temperatures would be an advantage in this respect. The required environment, as I say, can be aromatic or aliphatic. It can be a high or low sour gas content or sweet, and is selected from the tables provided. But in all cases, there is the possibility of using a bespoke environment as agreed between the vendor and the purchaser. Again, I would mention, as Alexandra has already drawn attention, both standards require a lifetime prediction to be made using erroneous type manipulation of the data. And of course, this pre-assumes that there is a single degradation process occurring in your material. And it also assumes that there is a linear or very near linear change in your properties with time. And as we shall see, that isn't always the case. So these are example charts taken directly from the ISO standard. And you can see that on the left-hand side, the selected property, you select a property, normally tensile strength, modulus, or elongation, and you set a failure criteria, which is defined normally as 50% loss of that particular property. That failure criteria is not a pass-fail criteria. It is simply a construct with which to calculate your lifetime. So you can see there at 3 temperatures, 1, 2, and 3, the properties decreasing as a function of time of aging. And assuming that there is a single degradation process and that erroneous applies, we're able to fit a linear regression straight line to these data. And we end up with an equation, which you see below the chart, describing the degradation of that material at that particular temperature. From that, we can, if we haven't, as Alexandra said, it's important to try to drive your aging test to cause 50% reduction in properties, and at least one of your temperatures should do this. For the other temperatures, if you haven't reached 50%, you can then calculate from your equation. Then we move to the chart on the right-hand side, in which the y-axis is the log, the natural log of 1 over the time taken to lose 50% of the property, and the x-axis is 1 over the absolute temperature. And if all other things being equal, we would find that we would get a relatively straight line. We'd have some kind of correlation coefficient describing how well our data fits that straight line. And we would then be able to extrapolate that, that chart further to the right to tell us the performance, the expected performance of the material at longer, at lower temperatures. So as you can see, the lowest temperature on that chart on the right-hand side is 210. This would enable us to forecast the lifetime, 50% lifetime for temperatures below 210 degrees centigrade. Of course, this is an estimation, and it doesn't take into account any factors such as applied load and so on. So this is a lifetime of unloaded material. So at this point, we have another poll question for you, if you would be so kind as to give us your thoughts on this one. And the question is, which is the most important criteria for predicting the lifetime of polymers, in your opinion? Is it A, environment, i.e. temperatures, liquids, gases, or pressure? The duration of the test is answer B. Answer C, the properties being measured. Or D, the definition of what the lifetime or half-life actually is. So if you'd be so kind as to vote now. Gives me a chance to drink a glass of water, and I would hope that there are some opinions on this. It'll be interesting to see what people think. As I have explained, I will be looking at the effect of duration of test, particularly, and properties being measured during these coming slides. So, Dan, I guess we'd be drawing this one to a close now. So we'll just wait on the results, and then maybe I'll need to change the next few slides depending on people's responses. So, okay, so that's very interesting. So 70% of the respondents have said the environment, the temperature, which is extremely important, of course. 7% have mentioned the duration of the test, which I will come on to in my later slides. 17% have said the properties being measured, and 6% have answered the definition of half-life. So that's extremely interesting, actually, and I'm relieved to know that I don't need to change my my slides too dramatically. So thank you very much for those. I will now, in that case, carry on with the presentation. So a few observations really about these test methods, and Alexandra has already pointed out a number of these kindly at the beginning. These are clearly set out test protocols, and they do enable comparison of a material performance under a common set of conditions. So it's a great way of comparing performance of different materials. The results may be generated in compliance with the standard, but as such, materials do not comply, they do not qualify to the standard. They are simply a set of results. And test laboratory certification for use at a temperature is basically meaningless unless some kind of duration is given. So if you have a report which says this material is good for 180 degrees use, that is fine, but it really needs a time attached to that temperature as well. So, as I mentioned, the other important point is that the failure criteria are solely defined to enable a material half-life to be estimated. They are not pass or fail criteria. So, in the following slides, I hope to be able to demonstrate to you how experimental data we've generated using these standards might provide either inconclusive or perhaps provide incorrect evidence of the polymer performance. I'm going to be using examples all based on Victrex 450G, which we have obviously focused on considerably over these years, but I'll also present, for contrast, in some cases, the performance of an experimental high-temperature PAEK, and I hope to demonstrate the significance of the choice of property which is being made for the evaluation, and also the influence of test duration. So you see now why I was keen to see the results of the poll earlier. We believe that these are two of the most important factors in the whole experiment. And then finally, I will show how additional experimental data which we generate at Victrex can be used to augment and support the data generated from these tests. So all of the data I'm going to supply is derived from tests which were carried out, in this case, the NORSOK M710 test protocol, both edition 2 and the current edition 3, which came in, I believe, last year. So I go back here to, I think, 2009, when Victrex first began to seriously evaluate the hot sour performance of its polymers. And we selected at this time 3 temperatures, 175, 195, and 210 degrees C. The sour gas content of the gas phase was limited to 2%. That was dictated by the test protocol. And we tested for 35 days at the lower temperature and 25 days at the higher temperature. And here's the data which we generated for these 3 temperatures. So looking first at the evolution of tensile strength, maximum stress over a period of time, we can see fairly flat plots. Very little change in strength over duration of the test. And in fact, at 2 of the temperatures, it does actually look as though the polymer is increasing with strength, and that it will go on getting better and better. But of course, instinctively, we know that that's not true, and that won't continue ad infinitum. But this is, as Alexandra has mentioned, very useful data for comparing between different materials. If we look at the evolution of strain, then we see more change. That's not surprising because strain is more sensitive to aging, typically, with a material like this. But we see that the correlations, certainly at the lower temperatures, are quite poor. There's not a lot going on which we can actually fix to this erroneous type degradation. And there is maybe a better chance of fitting a line to the higher temperature data. If we look at modulus, now due to the nature of semi-crystalline polymers, of course, as most people on the call will know, as you anneal a polymer, the semi-crystalline polymer, you will increase the crystallinity some. And so we see that the modulus is actually increasing in all cases, and that the kind of preconditioning treatment which is recommended by the standard hasn't really ironed out all of those pre-changes prior to any kind of degradation of the polymer. So this actually is giving us quite a confusing picture of what the material will do. And on this basis, I would suggest, and we'll come back to this, that modulus as a criteria for applying this test to thermoplastics is probably not a good choice of parameter to use. This is very much a useful property when considering the performance of elastomers, but I think there has been a considerable amount of carryover from one industry to the other. So our first observations then, after the completion of this edition 2 test, if I were applying the standard as as it's written on paper, I might then write a report which predicts that peak has a near infinite lifetime in terms of strength and modulus. Of course, that's something which experience and other experiments tell us isn't possible. I would also conclude that the strain is far more sensitive than strength or modulus to the aging process. And I would probably conclude also that overall the results are rather unreliable and are not very useful for predicting long-term performance of a high-temperature, thermally stable polymer such as PEEK. So I guess I'd need to ask myself then if the temperatures and aging durations which I had chosen were sufficient in this case. And hindsight is a wonderful thing, and with hindsight, my opinion would be no, I had chosen the wrong test parameters. However, interestingly and quite rightly, the test report from the laboratory used concluded that PEEK has a very long lifetime, up to 220 in this environment. Now, that's all that could be concluded, but it's far from sufficient for an industry which is looking for some level of precision now in terms of lifetime prediction. So now moving on to the more recent history, we have now tested to NORSOK M710 edition 3, and deliberately we have increased our temperatures. So we're now testing at 195, 210, and 225. And in line with the new protocol, we've increased to the high sour gas content of 10%. And quite deliberately, and along the lines that Alexandra has mentioned earlier, we have really tried to increase the test time. So we've gone up to 105 days of testing. So here is the evolution of stress at break over the period of aging. And you'll see that although the correlations are still quite low at the lower temperatures, you do have more measurable change occurring. You can see something happening which tells you that actually the properties are beginning to fall. There is still something of a kind of a muddle in this first few hundred hours of testing where you have different processes occurring in the polymer, and I'll come back to that in just a moment. The evolution of strain, as I say, it's more sensitive to aging, and so we expect and we do see considerably more change, and this does suggest that there is some kind of chemical degradation taking place. And although the correlation coefficients are not high, they are significantly higher than those delivered by the stress versus time curves. Once again, and coming back to my old friend Modulus, Modulus is doing all sorts of strange things at even at these different temperatures and different times. Once again, kind of supporting the notion that it's a confusing picture to use modulus for thermoplastics, and it becomes very difficult to estimate half-life of the material, the lifetime of the material, based on modulus alone. Now, I mentioned earlier that using an additional temperature is useful. One might expect that by adding another temperature, you're going to increase the accuracy of your experiment. Here is the data we've now added in 240 degrees. So it was all done at the same time, this testing. I've just added it in here just to show the relative difference that this makes. You see, interestingly, at 240, we have a correlation coefficient which isn't too bad, but it does suggest that, again, there's something maybe going on earlier in the test, which is perhaps upsetting the results. But in any case, we would expect that the improved correlations at elevated temperatures might lead to a better estimate of the lifetime. So, in this slide, I'm going to show. I'm not going to bore you all with the manipulations of the data, but we've use the erroneous approach using the straight lines you saw in the previous charts to calculate a lifetime at a range of temperatures, noting that the highest temperature needs to be the highest temperature tested, certainly no higher than the highest temperature tested. And we're going right down, we're being quite brave, and we're going right down to predicting at 130. And my first comment would be, and there is a decimal point in here, and as Alexandra said, this is well beyond what I think erroneous would have expected. The standard doesn't actually suggest anything around calculation of error and potential errors in the data. That's something which needs to be considered further and needs to be discussed between buyer and vendor. However, you will see that this data is telling me that my tensile strength of peak is going to have reduced by 50% in 1 year, approximately at 220, and then going down to say 180, that process would take 40 years. Now, I then add in the results taken from 4 data sets. 4 data sets we know statistically provides better correlations, and interestingly, it provides a reduced lifetime prediction. So in some cases, that's reducing by nearly 50%. However, my sense would be that this is a more precise estimation of the lifetime of the material. So, again, taking the same range of temperatures for lifetime estimates and using the same set of tensile strength data, lifetime that is, that's the lifetime to lose 50% of the tensile strength. This is the data actually generated from 3 temperatures. I would now compare with the lifetime generated from my strain data. So I make the same manipulation with the data, and you'll see that I end up with a significantly lower lifetime from using my tensile strain at break data. So if I go back to that 180 degrees centigrade forecast lifetime, 40.3 years to reduce the tensile strength by 50%, but only 1 year to reduce the tensile strain by 50%. So it's very important here to note that the parameter you're measuring has a significant effect on the lifetime. And if strain is the parameter which is critical in your proposed application, then you shouldn't be looking at the lifetime generated from strength data, because it can provide a significantly different result. Interestingly here, I've put in my best possible attempt from the rather scattered and confusing data from modulus, and this, at lower temperatures, unsurprisingly, I guess, sorry, at the higher temperatures, it comes out fairly close to the other quantities, and then at the lower temperatures, somewhere between the two. However, I don't think that the statistics would allow me really to use the modulus data for any more than just looking at trends in what the actual modulus is actually doing. I mentioned a few moments ago how the beginning of the curve is rather confusing at some points in time. And as I mentioned, with a semi-crystalline material such as PEEK, you do get aging effects which happen at the beginning of the test because it's being annealed effectively at high temperatures, but it's also absorbing hydrocarbon fluid. And both test standards do allow for a conditioning treatment of the material, which is basically a few days at temperature in the hydrocarbon, which allows the material to absorb hydrocarbon, to become saturated, and then the sour gas is introduced into the test and would begin the chemical degradation process. However, this is something which depends very much on the type of polymer you're using. And in the case of peak, one could argue that actually those changes in crystallinity and so on are continuing, excuse me, are continuing significantly further than those couple of days. So it's this region here which is the one which is kind of the one in question, really. So one option we could take would be to use to extend our kind of conditioning period to, say, 500 hours, something like that, and then try to fit some kind of plot to the data which follows that time period. This isn't required by the standard. This is just another way of examining the useful data which we have received. If I do that, then my correlation of my data increases significantly from 0.8 to 0.93, which is reassuring. I've taken out some of the uncertainty, and then if I look at my my lifetime predicted, so this center column is my lifetime predicted from all the data after the 500 hours. So that's taking out all of the sort of the annealing effect, or at least trying to take out those annealing effects. Then you see that again I've significantly reduced my lifetime prediction down to, again, if I look at the 180 figure, I've come down from something like 30 years to something around about 12 years. But again, one might argue, and it's, at this point I would just be suggesting these as thinking points, but one might argue that this data for peak in particular might be more realistic to consider. So moving on to the next part of the presentation. Test duration is very important. Alexandra mentioned this in her slides, and certainly it's something which I would like to focus on. The duration of a test should be as long as you possibly can make it, and it would be great if we could test all materials for as long as they were going to be used, but that's clearly not possible. And actually generating long-term data, I think, is quite unusual. Short-term data isn't useful, but NORSOK and ISO are frequently seen as a kind of a task, a pain, really, that has to be borne in order to sell into the oil and gas market. And certainly the maximum duration of test data, which is common to see, would be around 35 days at the lower temperatures and about 12 days at the highest. The problem is the test is only as good for as long as you take it, and you just don't know what's going to happen afterwards. You can make some intelligent guesses, but you don't know what you don't know effectively. Before I get into Donald Rumsfeld and all of that, I will move on to the next slide. So what I have done in this slide is I have terminated the data you've seen previously for lifetime based on tensile strength, loss of 50% of tensile strength. That is this central column here. But I have terminated my data 3 points earlier, sorry, 2 sampling intervals earlier. So I've restricted now my data to 1400 hours maximum. And you can see that by feeding that data into the erroneous manipulation, I have a significantly higher estimate of my lifetime. So again, looking back at that 180 degrees, my long-term data predicted a lifetime of 40 years. My short-term data, and I'd add that this short-term data in this case is still longer than what the industry tends to use as a standard, is predicting 102 years lifetime. So a very significant overestimate of what we know is the case from our short-term, from our longer-term test data. Another example of short-term data. So here is modulus. Despite my protestations about using modulus, for some reason I've let one of those curves creep into my presentation. But here is a modulus chart over 500 hours, comparing the performance of 450G with a high temperature experimental peak, which we manufactured at Victrex. That's the 500-hour data, and this isn't a construct for the purposes of this presentation. This is actually what happened. So at 600 hours, the modulus dropped very significantly. Clearly, there was the activation of a chemical degradation was sufficient that at the sort of 600-hour period, the material was just too brittle to actually test. So 500-hour testing clearly doesn't give the whole picture, and wherever possible, the testing should be extended for as long as possible to get a good picture of what's actually happening. Now, you might argue that you just don't know how long you're going to take your test in order to find out what's happening, and that's a perfectly reasonable argument to make. But I would argue that there is a lot more that can be done to augment and support the experimental data generated from test protocols such as ISO and NORSOK. And one of the things we do at Victrex is we look at residual viscosity of the polymer, which is a great indication of molecular weight, to tell us what changes are actually occurring on a molecular basis. So in this chart, you'll see the blue line. This is an aging at 220 degrees centigrade. This was a 20% H2S environment. It wasn't, strictly speaking, a NORSOK protocol test, but it was done according to the NORSOK testing standard. And our samples were sitting specifically in the aqueous phase. If we look at the blue chart, which charts the tensile strength as a function of aging time, you'll see that we start off around 97, 98 megapascals of strength, which is where we'd expect to. We have some annealing, some increase in crystallinity, and then over a period of time, the strength maybe begins to drop a little bit, and at 1,000 hours, we have ended up pretty much where we started. So I might conclude, if I was just looking at that data, that peak is fairly resistant and that there's not a lot actually happening. But when I superimpose my residual viscosity data, which is effectively equates to molecular weight, you can see that there is change occurring from the very start of the test. So we would suggest that this kind of data is extremely useful for helping to understand how long you need to take your test, your aging test, to go on before you can see changes in mechanical properties. You know, you might look at this blue chart and say, okay, well, there's not a lot happening. We'll cut it off there at 1,000 hours. But if you look at the change in molecular weight, that would suggest that there is chemical change happening, and that at some point we are going to see more dramatic change in terms of the mechanical properties. So it's an important addition, really, an important addition to the armory to be able to understand the degradation of your particular polymer in question. One other mention, I just wanted to show how at Victrex we're going a very large step further, actually, in evaluating degradation mechanisms to help us understand how our polymers perform in aggressive environments. And we've been working with the Hartree Centre in the UK on creating a quantum mechanical model which uses a thermodynamic approach to predicting the reactions of peak polymer with various reactants. And this is, I have to say, this is beyond my brain, but what this actually does is it creates an energy map, and you can see that the high energy states are colored in red and the low energy states are colored in blue, and this therefore predicts the resultant products which you would get from any interaction of the polymer with an environment. And we've done this so far with our peak HT and our peak ST polymer, and we've done that in relation to its interaction with the water molecule, and it provides an extremely good correlation with reality. So this is, again, useful in as much as it helps us to, as this goes forward, it will help us to tell our potential customers about how a polymer might react with chemicals we haven't yet tested in the laboratory, but it also will enable us to understand how new polymers might interact with an environment before we've even made them, which would accelerate the time we bring them to market. So finishing up now, a few conclusions from my side. I would say that NORSOK and the ISO standards are all excellent standards for assessing performance of polymers. However, care needs to be taken to select the most appropriate property parameters for evaluation, rather than just defaulting to the norm, and that the lifetime for one property might significantly differ from another. It's important, as I hope I've demonstrated, to show that the aging period needs to be long enough to ensure that any possible degradation mechanisms are observed, and it may be necessary to use other means such as residual viscosity or GPC to increase the assurance for the customer on this. And finally, that I'd like to mention that early termination of aging can lead to very significant overestimates of lifetime and the maximum usage temperature. So I hope that we've communicated that certainly at Victrex we believe we're leading the way in developing lifetime assessment for PEEK and other polyaryl ether ketone polymers. And I would urge you to think and look for the same level of detail and information wherever you source your polymers from, and whatever those polymers actually are. And with that, I have finished the presentation, so I think there's still some time for a few questions.
Yes, absolutely. So thank you very much for that, Jeff, and also to Alexandra. As Jeff mentioned there is some time today to field a few of the questions that you've been posting via the Q&A box on your WebEx app. So there is also some time to file one or two other questions if you have them. Please use the box provided. But to kick off for both of our speakers today, address the questions, we'll start with this one. Does the remelting or processing of polymers impact the performance in lifetime testing?
Okay, so I would say that any process which involves remelting of the polymer will potentially change the structure, especially if it's a semi-crystalline polymer, would change the structure sufficiently that a retest would need to be done. So, for example, if Victrex generate data according to these tests in a particular environment, and then that same material is taken away and used by another user, which involves melting, they have the scope then to process the material in a different way, maybe ending up with a lower crystallinity, something like that, and that would provide significantly different results. Alexandra, do you have anything to add to that one?
No, I completely agree with you. And even if you're not melting, if you're processing, I think you will get different mechanical properties, and life estimation based on those mechanical properties may change because of the processing, the crystallinity, and these kinds of things. So processing is definitely something to be looking out for when you're reading these results, so that you make sure that you're testing the right stuff according to what you need to use.
Great. Thank you very much, both of you, for that. Moving on to the next question. Did you first do thermal aging characterization before increasing aging up to 10% H2S?
That's a very good question, actually. So we have done thermal aging alone, thermal aging experiments alone, in order to assess the kind of temperatures which we would need to begin to bring about measurable change in the peak polymer. So that kind of contributed to the choice of aging parameters, which we then used in the second set of testing to the revision 3. Having also seen and done a considerable amount of work using 2% H2S, which is from revision 2, we recognized that we needed to significantly increase the level of H2S in order to get measurable change. And in fact, we actually ran a whole series of experiments with 100% sour gas in the gas phase to try to understand which kind of combinations of parameters would give us measurable change and enable us to give meaningful information back to our customers.
Okay, great. On to the next question. Is an increase in crystallinity ever a problem in field applications?
Oh, that's a very good question. So increasing crystallinity will increase the strength of a semi-crystalline material like PEEK. It will increase the strength, and it will increase the modulus of the material. And there may be a very small decrease in the elongation at break. However, generally speaking, those changes would be, in my humble opinion, it would not be that those were an issue for the industry. I could never see that as being a significant problem. Many of the applications of PEEK, for example, in areas such as sealing, backup rings, and so on, the increase in modulus and strength is probably, if anything, might be slightly advantageous. But I certainly couldn't see it as a problem.
Okay. Next question. Could you discuss the relevance of testing entirely above TG and extrapolating below TG? And the comment here being that might it be more relevant to run aging tests above and below TG, as activation energies will be different?
That's a really excellent question, and I kind of had left my 130 and 140 degree predictions in those tables deliberately to try to fish that one out. So thank you, whoever raised that question. I would certainly agree that if I'm aging my material above TG, which of course I have been, it would not really be reasonable to predict, to extrapolate through the TG, because the activation energy would change as you go through that TG point on the way down. So really, if the standard is going to be applied properly, if I'm testing above TG, I should only predict down to maybe 150 in the case of PEEK, which has a TG of 143. And then if I want to see how the material performs below, I would test maybe at 3 temperatures below my TG and then go below that. The problem, of course, with a polymer like PEEK is that I say it's a polymer, it's also a great benefit, but it is so chemically inert and thermally stable that I would be, well, I nearly am an old man, but I would certainly be a very old man by the time we actually saw any change in the laboratory. And therefore, yeah, it's you paid your money and you makes your choice. But the point raised is a very good one, and I completely agree.
Fantastic.
Yeah, I guess from my point of view, the only suggestion I would have is to, if you want to truly test below the TG of a material like PEEK, is to look at different types of chemical degradation. So maybe increase the H2S levels or increase the aromatic levels or something like that, so that you're driving your correct chemical change even at temperatures where you don't normally expect a reaction to occur.
Yeah, that's a very good point.
Right. And yes, we are running ever so slightly over, but there are so many great questions. I think we should make time for one or two more. In terms of the next question, I've been hearing a lot of noise around cross-linked PEEK polymers lately. How would these perform in the tests that you just went through?
That's a very good question. Actually, we have looked at cross-linking ourselves. It's difficult to say. I guess I would just simply point out that any chemical resistance data that I was looking at in these kind of environments, I would want to see that those tests had been run over certainly a sensible period of time, something akin to the period of time which I've shown here for PEEK, for 450G, to ensure that yeah, any kind of chemical resistance data is valid.
Okay. Great. And maybe time for just one or two more. Like I said, I feel we need to squeeze these in. These are some great questions.
Please do.
Could you comment on the testing under closed system conditions, i.e. Fixed content of H2S in an autoclave test versus the number and volume of the specimens?
Could I get your opinion on that one, Alexandra, first of all?
Well, it specifies the closed system in the standard, and there are some pros and cons to that, I think, because, and I think it's also a current debate going on whether or not to top up the fluids when you take samples out, because if you have a closed system, that means that at some point you're going to start eating away at your reactants if you have a relatively small volume of fluid to number of test specimens. So there is some language in the standards that actually says, I believe it's 25:1 or something, the ratio, to make sure that you have sufficient fluid. But in reality, a lot of these materials are sitting in applications where they're not getting fresh fluid all the time because they're sitting behind some metal seal, or they're sitting in some space-limited area where they're not completely refreshed at all times when the well is flowing. So there is it's a benefit for the material to have a reduction in reactive species, but it's also not completely out of the realm of application to have that scenario. And just completely driving the reaction with constantly renewing the fluid also may introduce oxygen, which is not a relevant species and does actually have quite a reactive, aggressive behavior in some of these tests. But it's a good question.
Great. And then finally, I think we should make time for just one more question. Did you perform any thermal analysis of the tensile specimens after aging to see if there were any trends?
After tensile testing, we have, as I showed, we had done various kind of grinding them up, dissolving them in sulfuric acid, and measuring residual viscosity, which gives us a feel for the molecular weight change. We would also, we have also made sort of thermal analysis looking at DSC charts and seeing, seeing the indications, looking at remelting peaks, for example, seeing the indications of degradation, and that is quite a useful tool. Again, it's one of those things I referred to in the slides as being a useful tool to sort of augment the data you're seeing. So if after your aging period you take a sample out and you don't see a lot of change, but you can do a DSC on some of the material, you may see that there is some indication of degradation by looking at the DSC charts, and that again would indicate that you needed to keep your test running longer to see some kind of change in mechanical properties. So it's a good question. I'd have to say we haven't actually made a systematic study in that respect. So we tended to look at sort of the beginning, the middle, and the end of the experiment, rather than sort of a very pragmatic analysis of what we see. A great question. Thank you for that.
Okay, great. Thank you very much. And yes, like I say, many great questions today, but I'm afraid that's all we have time for today. Apologies if we didn't get around to your question, but shortly after the webinar, the team will do their best to get back to each of you individually to answer your query, so thank you for your patience. Thank you again to Jeff and to Alexandra and to all of you for joining us. We hope you found the session useful, and thank you for your valuable comments, questions, and polling responses today. Please also remember that proceedings will be made available as soon as possible for all registrants. Details will be sent out shortly for access to those. If you've made other queries, if you have any other queries about webinars or other services provided by Smithers Rapper, please get in touch with me directly. And after leaving today's webinar, you'll be presented with a brief survey. We'd love to get your feedback, so please take a few moments to respond. And with that, I'd like to thank you all for joining us and say goodbye.